All right, so we're looking at the first question from FRQ Friday number 8. I'm not going to go through reading the question because you should have it sitting right in front of you on your sheet. I'm just going to talk through how you should have worked through it and where the points would have come from. So on A, they're looking for an estimate for W prime of 12. Well, W prime would represent the derivative, which is rate of change. But since we don't have a function to work with, the way that we would get the value for the rate of change would be to estimate it by finding the average rate of change. And if we're wanting it at 12, go look at your table. Your table doesn't have time 12 in it, and even if it did, we wouldn't use it. You would use the time right before 12 and the time right after 12 and find the average rate of change between those two. So it's simply slope. So W prime of 12 is going to be 67.9 minus 61.8 over 15 minus 9. And then you just simply calculate that and you get 1.017. So you got a point for coming up with 1.017, but then it also says using correct units, interpret the meaning of your answer in the context of this problem. Well, if you think about what you were calculating, you were doing degrees Fahrenheit divided by your time, which is measured in minutes. So degrees Fahrenheit per minute. Just looking at the units alone tells you that that's a rate of change. So the way that you describe this in the context of the problem is you would say W prime of 12 is the rate of change of the temperature in degrees Fahrenheit per minute, and you do have to specify at t equals 12 minutes because it's not the rate of change all the time, it's the rate of change specifically at 12 minutes. So you got a second point for that. So part A was worth 2 points. Then part B. Part B says use the data in the table to evaluate the integral from 0 to 20 of W prime of t dt. Well, the information in the table is W of t. So we have to kind of think through what we're doing. If we're integrating W prime, well, W prime is the derivative. So the integral of the derivative would mean that W prime came from W. So using our integral notation, this is what it would look like when we integrate it, because W prime is the derivative of W. So when we integrate it back or do the antiderivative of W prime, we get W. And then remember the way that we calculate that is we substitute upper minus lower. To find the values for W of 20 and W of 0, we simply look up at our table. W of 20 is 71.0, W of 0 is 55.0, and so your answer is 16.0. Now, also think about units again. We're just taking the W's. The units are still going to be the units for W, so degrees Fahrenheit. So when it says using correct units, interpret the meaning of this in the context of the problem. Well, what is that 16 degrees? If you think about what you just did, you just found the difference from the temperature at 20 minutes to the temperature at 0 minutes. So this represents the integral from 0 to 20 W prime t dt is the change in temperature from t equals 0 to t equals 20. Minutes. Oh, and you want to include your units, so somewhere in there you need to say in degrees Fahrenheit. Okay. Part B was also worth 2 points. 1 point for getting the 16 degrees and 1 point for correctly describing what that integral represented. All right, then part C, this is where we get into the Riemann sums. They want us to use a left Riemann sum with the 4 subintervals indicated in the table to approximate 1/20th of the integral. Now the Riemann sum is only going to approximate the integral. So you have to remember to incorporate the 1/20th before you're completely done. So I'll just start with finding the integral. So taking the information, make sure I have enough room, that's up there in the table, notice that my times are not equally spaced. So my first interval of time goes from 0 to 4 minutes. It is 4 minutes wide then. And if I'm doing a left endpoint approximation, I'm going to use the first W value for that interval. So that would be times 55. Then my second interval goes from 4 to 9. So that change in time is 5. The left W value for that interval is 57.1. Then we go from 9 to 15, which is 6 minutes wide, and the left endpoint is at 61.8. And then from 15 to 20 is 5 minutes wide, and the left endpoint is 67.9. That's your setup for how to calculate the left Riemann sum. This is where your calculator comes in handy because you could just calculate all that real quickly in your calculator. You would get a total of 1,215.8. But what you have to remember to do is then take 1/20th of the integral. And you get 60.79. And then they ask, does this approximation overestimate or underestimate the average temperature of the water over these 20 minutes? Most of you did pretty well on this portion of it because you remembered if the function is increasing, then LRAM will be an underestimate. And that's all you need to say for the explanation. You would say, this is an underestimate. Because LRAM always underestimates when the function is increasing. So you would need to say underestimate and increasing in there in order to get your credit for your explanation. So this part of the FRQ was worth 3 points. You got 1 point for setting up the LRAM correctly and like showing that setup. Your answer couldn't just pop out of nowhere. And then you got 1 point for the correct answer of 60.79 and then 1 point for the explanation there. So 3 points for part C. And then that takes us to part D. So part D gave us a function to model the water temperature after time 20, from 20 to 25. So it says, based on the model, what is the temperature of the water at time 25? So if the rate of change is at W prime of T, to find the total amount of change in the temperature, we would integrate from 20 to 25. Now we only go from 20 to 25 because this function only applies to that interval of time. So we can't use it all the way from time 0, okay? So that's how you find the change in the temperature. Now, I'm going to pull up my calculator real quick and type that in because some of you had that written correctly on your paper, but for some reason your answer did not come out correctly. So first thing you want to do is you want to make sure that you're in radians because there is a cosine in that function. And so if you're not in radians, it's going to mess you up. That may be some of your issue. And then we're going to do math 9. From 20 to 25, and my function is 0.4 times the square root of, we're going to put an x there, and then times the cosine of, I can't read, 0.06x, close the parentheses on the cosine, and then put a dx. So maybe you messed up with where your parentheses were, maybe you weren't in radians, I don't know. But this is what you get when you calculate that, 2.043. So going back to here, now does that mean that my temperature at 25 minutes is 2.043 degrees? No, that means that's how much the temperature has changed since the beginning of the time interval. So you had to include the fact that initially that temperature at time 20 is 71 degrees, because that's what it says in the table, is that the temperature at time 20 is 71 degrees. So that means that your temperature at time 25 would be the sum of those two things, so 73.043 degrees Fahrenheit. So you got 2 points for part D. You got 1 point for setting up your integral correctly, even if you got it wrong because you weren't in the right mode or whatever, and then you got 1 point for the correct final answer there. So that's problem 1 from FRQ Friday number 8.